It's been a long day, hasn't it? How many people were like, 10 sessions at the same time? I want to go to sleep. That's how I felt. So you're probably wondering, what the heck is workload isolation? And why are we talking about it? And am I doing it wrong? Or are you doing it wrong? Even though I need no introduction, I will introduce myself. So I'm a lead product manager for MongoDB Server. I've been working with MongoDB for coming on 7 years, and been working at MongoDB, the company, for almost that long. But before that, for good, 15, 20 years, some were good, some were not so good, I worked with just about every other database known to man. In fact, I think the only ones I missed was like Microsoft and IBM. I don't know why, somehow I was spared those, but I've worked with pretty much all of the others. So databases, in a lot of ways, they're the same. The problems tend to be kind of similar. So every year, sometime in January, sometimes even earlier, I start thinking, what am I going to talk about at World this year? My first World was back in 2014. I talked about diagnostics and debugging because that's what I wanted people to have more insight about. Last year I talked about the aggregation pipeline because I love how you can do really powerful analysis with it. I wanted other people to know that too. And this year I was like, I'm ready for like a really lighthearted year. So I just wanted to do a talk on disaster stories. Because everybody loves disaster stories. Everybody loves disaster stories because, well, partially you figure that you get a chance to learn from other people's mistakes, right? So that you don't have to make them yourselves first. But partly also because, it's fun. I had great titles. I was going to call it 7 Deadly Sins of Bad MongoDB Deployments, or possibly, if 7 was too much, like 5 Stages of Grief of Bad MongoDB Deployments. But then people said, like, that's really negative. You want to be, like, positive, like, what should you do, not what shouldn't you do. So then I was going to do, like, the 10 Commandments of MongoDB deployments, of good MongoDB deployments. And that all seemed like an awful lot of work. So instead, I kind of started thinking, why is it that we're compelled to, post-mortem disasters in such detail? What is it that these disasters have in common? Or what is it that the disasters that people recover from more easily have in common than the ones that cause like prolonged downtime? When discussing this with colleagues and other friends, I of course realized that the reason people love disasters is because they're happening to somebody else and not us. And that's fun, because you go, I've done some pretty boneheaded things, and trust me, I have. And it's nice to know that somebody out there did something at least as bad, which I promise you, from the stories that I'm going to work into this, it's highly unlikely that any of you have done anything worse than what some of these people have done. So you also need to have cool pictures to be able to give a talk, so that's always important, cool titles, cool pictures. You also need to do research, so I did research. I Googled most common causes of data loss, most common causes of outages, database outages, or technical problems. And I found a chart, and as soon as I found it, I stopped. I don't know if it's worth anything. Somebody might have just made up those numbers. But it seemed pretty plausible. More than one answer could have been given in the survey. So for example, I certainly hope that fire is considered a server room issue, right? And usually unscheduled updates and patches are part of human error, right? That's why they're unscheduled. We forgot to schedule them. So, right, so how do we avoid being one of these stories that's up here? And what can we learn from this, right? Now, the way I'm using the phrase workload isolation is not the way that you'll sometimes see it in our documentation, or the way Elliot was talking about it at the keynote, which is about sending, for example, reads to designated secondaries, right? That's just like you tag things. You're responsible for this workload. You're responsible for this workload, right? Or zone sharding. I'm not talking about that. I'm talking about how to keep problematic things completely away from other things. In other words, if something bad happens over here, let's say a fire, how do you keep it from bringing down every app that you're supporting? And I love analogies. If you've ever heard any of my talks, I like analogies. So I kind of thought about it, and I thought of something from my past that I could make an analogy with. So for those of you who are too young to know what this is a picture of people playing in a bridge tournament. So I used to play bridge when I was much, much younger. And in fact, it was so long ago that back then they allowed smoking. If you look really closely, it's like a dude smoking a pipe. There's ashtray on every single table. And those of us who didn't smoke and who hated smoke always complained about it. So the compromise that was reached is every other section would be a non-smoking section. There's about 10 sections in there, and they're alternating smoking, non-smoking. How well does that do isolating those of us who didn't want to be near smoke from smoke? Not very well. In fact, sometimes in small tournaments, it would just be every other table would be smoking and non-smoking. So this is the wrong way to do any isolation of bad things from things you want to protect from them. This is kind of like our usual stuff I mentioned, right? Reading from secondaries, you tag secondaries so that you can read from them without worrying about them also having to serve OLTP-ish traffic, right? How do you keep that separate? Well, you tag them, you designate, you say they're priority 0, right? Or read-only secondaries. You can't be promoted to a primary because you're running a really long, slow ETL query on it or something like that, right? Zone sharding says, and I'm not necessarily talking about geographical zone sharding. Zone sharding can be used to move data to particular specific shards that have different hardware, right? So you're saying, okay, your old data, I'm isolating you here on old spinning drives, and my new data or recent data is going to be, let's say, on SSDs, right? That's a form of workload isolation. Our docs talk about all that. I'm not going to talk about that. I'm going to talk about keeping things separate so that if you do have a disaster, no, wait, let me rephrase it, so that when you do have a disaster happen, because I guarantee you everybody will, some point, somewhere, cause some kind of a disaster. We are usually our own worst causes for that, but sometimes these are things that just cannot be prevented, right? Whether it's physical failure of something or human failure of somebody else, right? So I thought about what is it that isolating workloads from each other helps with the most? And I thought of a few things. So the most obvious one that jumped to mind is scaling. And when I say scaling, I include under that performance, and I include under that capacity planning. And I'll show you a pretty detailed deep dive that I did myself to kind of prove that it really makes a big difference to your ability to have good performance and good planning. There's also availability, right? Recoverability. If something's on fire, it's not available. If you lose data, you have to be able to recover it, and the quicker you can recover it, the quicker you can be back up. Security kind of comes in there as well. I made up another word. I don't know if it's a real word, but debuggability. Debuggability. That sounds like a word to me, right? The ability to tell what's happening and what you need to do in reaction to that is kind of important. So I'm going to tell some stories in between some technical points, and they're true or based on stories that are true, inspired by stories that are true. These are based on real cases that were filed with MongoDB support. I may have embellished some, or I may have combined some in order to make a point in a more succinct way, which you'd never know because I'm not usually known for being succinct. No names will be included, names changed, pronouns changed. Draw no conclusions from any pictures that you might see because they're all made up. And I omitted some details for the benefit of brevity, but just the boring ones, not the really embarrassing details. Embarrassing details I find are usually most educational. So here's a typical example of one of these cases. I call it the case of the mistaken delete. The subject of the case that was filed was we accidentally removed an entire collection. Is there a way to undo? Right, so somebody was at the shell and they meant to type db dot the name of the collection, remove, and then a specification that matched a single document. And they accidentally left out that specification and they just said remove, and that removed the entire contents of the collection. Why? Why did we make remove work that way? Probably because we were inspired by the precedent set by SQL, where if you say delete from table and you leave off the where clause, it says, oh, I guess that matches everything, bye. So, yikes. So this was a simple typo, caused a bit of a disaster. Luckily, they were running a replica set. Now, there's one problem with the replica set. When you type something and it takes an action on the primary, it goes as fast as possible to try to execute that same action on all of the secondaries. So of course, the remove was replicated to all of the secondaries, but the replica set has this thing called an oplog. And if you have a very large oplog, or in particular in their case, this was not a very heavily written database, so the oplog had a lot of history in it. In fact, in their case, 45 days. So some of you guys might know that if you can restore a backup that was from anywhere during that time period, you could replay the oplog up to, but not including, the start of those deletes and get back your data. The only problem was their oldest backup was more than 3 months old. So this is where they did save the DB files. The recovery was not for the faint of heart. We did manage to recover their data from free lists, but it took a lot longer than it needed to. I don't know how many other systems they may have had. All of the systems that were using that particular database, though, were down for the duration of the recovery effort. Now, we can draw a few conclusions from this. One of them is replication is not the same as backup. Replication gives you a secondary node that you can take backups off of, right, without impacting the primary. But if you don't take those backups, you'll have nothing to restore, right? So do regular backups. Don't run production operations ad hoc, right? To me, actually, a bigger lesson from this is you shouldn't be sitting at the console on your production system and typing something and hoping that you don't make a mistake, because that's exactly when you'll make a mistake, or next time, or the time after that. I've done that. I'm sure we've all done that, usually like at 2 in the morning. So I was originally going to call the talk of disaster stories no SQL not equals no DBA. You hear people say, oh, everything is hosted for you, database is a service, you don't need a DBA. You don't need a person whose title is DBA, but you need somebody to wear that hat, or at least occasionally put it on and say, are we doing backups? And if not, are we paying somebody else to do our backups, right? Things like that. This is not specific to MongoDB. This happens with all databases, right? I went to do some research for this talk, and I found my favorite Stack Overflow question ever, and it's this one here. I accidentally deleted a row, but I found a solution how to restore it. So I tried it. I tried it on a backup taken after the delete. That person may be applying for a job with you or us or somebody else here shortly. And they'll know that there's a process. They just didn't quite understand it. So, by the way, because of that case, in the shell, the remove helper now requires an empty document. It will no longer accept nothing as input. It'll say, if you really mean to delete nothing, to delete everything, match everything, pass us an empty JSON document. Small, tiny thing, but... So, that was not related to scalability, that was related to disasters. Scalability or capacity planning or performance or how much money your hardware costs. Things generally go something like this. You start out with a replica set, you have your application, then things grow, you might shard some more, then you add other applications and they're using the same data, and then another application, and meanwhile your data is growing. So you have more data, more data, more data. And I kind of split them up into 3 different ways to partition that data onto those shards, replica sets. So the first way I call shard everything. So you partition everything. Usually it starts out by you saying, oh, I got to partition my largest collection. So you partition it, and it's evenly balanced, but now the primary shard for the database has all the unsharded collections. And you go, well, that's getting more work than the other ones. I better just shard everything. And pretty soon you're sharding even really tiny collections just because, like, oh, it's same script, does it for all of them, it's good enough. I call this scenario 1, shard all the things. So we're going to keep that in mind as scenario 1. Scenario 1 is very easy up front because you don't have to think, right? And you always know where all of the data is. It's always on all of the shards. Scenario 2 is you decide to partition the data, but you try to do it cleverly and limiting subsets of data to subsets of shards, right? So maybe you have a specific collection or database one per shard if you have a lot of smaller databases. If you have to shard some of the larger collections, maybe you use tags to limit them to a subset of shards. So I'm going to call that scenario 2, shard some things, sort of, sometimes. It's kind of the in-between 1 and 3. And 3 is, notice that the sharded configuration went away. Each one of those is shard 0, so it's just a replica set. So each set of data goes to its own replica set, and then you independently decide when that particular replica set needs to scale and needs to shard. I call that scenario 3, which is multiple replica set. It's not a shard nothing, it's a shard later, right? So good news is this is the configuration that, in my opinion, is best at achieving workload isolation of the type that I was mentioning that might minimize disasters and allow you to more easily observe what's going on each replica set. In order to kind of support my claim, which hopefully you believe, but I'll prove it anyway, I want to talk real quickly about horizontal scaling and how it's meant to work in MongoDB. So horizontal scaling in MongoDB we call sharding. And the ideal world, you would see linear scaling. In other words, as you increase the number of shards, the workload that you can handle should increase linearly proportional to it, maybe with some small fudge fact. Everybody know how sharding works? You're either too sleepy to say yes or too embarrassed to say no, so I'm going to review it anyway. In a sharded cluster, and this is a tiny sharded cluster with only 2 shards, for the illustration purposes, a request, let's say a query, comes to the MongoS. S stands for router. We're not good at naming things, but let's just say it stands for sharding router. And the MongoS will figure out which shard it needs to go to based on the value of the shard key. Then the shard actually does the work. The shard does the actual query, returns the result to MongoS. MongoS returns that result to whatever process asked for the query. This is if MongoS can target the query at a single shard. Sometimes a request comes in and it doesn't have the shard key in it, which means it needs to be broadcast to all the shards, or maybe it has a wide range of shard keys that cover multiple shards. So we call those scatter-gather queries because MongoS has to send them to all the shards, or both the shards here. Each of the shards does their portion of the work, returns the result. MongoS now takes the results and needs to merge them, which may involve more work or less work, depending on if there's any sorting or some other aggregation involved, and then returns the result. So what happens if 2 requests come into MongoS? Well, in a perfect world, let's just say that one of them, the pink one, goes to the shard on the right, the blue one goes to the shard on the left. The shards do the work, the shards return the result, and the MongoS just has to be sure to return the correct result to the correct requesting process. Scatter-gather, targeted. Notice anything? The shards seem to be doing more or less the same amount of work, but in one case, the system processed 2 queries, and in the other case, it processed 1 query. So my claim, my assertion, my claim that it is a fact that in order to achieve linear scaling in your sharded cluster, your queries, your operations must be targeted. They cannot be scatter-gather. Does that seem like a true fact? Yeah, okay, I see a lot of heads nodding. Good, so I'm not going to have to yell. I'll just show you a table. So if your application sends 10,000 queries to all the routers, and those routers are targeting those queries to individual shards, by the time you have 10 shards, each shard only has to handle 1,000 queries. If every query goes to every shard, no matter how many shards you add, each shard still has to do 10,000 queries. A different way of looking at it is, if each shard has the capacity to process 10,000 queries per second, minute, whatever, right, then with targeted queries, your system of 10 shards can handle 100,000 queries. But if they're scatter-gather, you still can only handle 10,000. Even if you had 100 shards, you would only be able to handle 10,000 queries total because each one would go to each shard. It's essentially you double your capacity of shards And you also double the number of queries that has to be handled if every query has to go to every shard. So that's throughput. Throughput's definitely going to be better. Now, what about latency? Latency, now you guys remember throughput versus latency? I gave a talk about that in 2015. Right? Throughput is how many you can handle during a particular short stretch of time. Latency is how long each individual request takes round trip. So with latency, so let's say one of your shards is under the weather. My PowerPoint drawing arts skills, everyone, yay. So shard over there is under the weather. And those two requests came in, and the pink one went to the healthy shard, and it comes back right away. And the blue one went to the ailing shard, so it takes a little bit longer to return. So in a targeted query cluster, the latency when one shard is not doing well is generally only going to impact the queries that are going to that shard. If every query is scatter-gather, one of the shards is ailing, what happens is right at 0.5 when MongoOS is merging the results, it's going to have to wait until that slowest shard returns its results. So at this point you're all going, make a note when I come back and check that our sharded cluster does not have any scatter-gather queries. Right? Right. So yeah, what happens is with scatter-gather queries, your latency is always the latency of the slowest shard of all of the shards. So if you have 100 shards, the slowest one determines just how slow each scatter-gather query is. Yikes. Disaster. See, I told you there would be a disaster before we were done. All right, so cool. So we think targeted queries are better. We think scatter-gather queries are bad. I didn't use any scatter-gather queries in my benchmarks. I kind of take it without any proof that they clearly don't scale as well. So, next, what scales better in absence of any scatter-gather queries? What if all of our queries were targeted? In fact, what if our queries were optimized to the max? Would there be any advantage then to isolating each subset of data to its own cluster or to its own shard versus sharding them across multiple? And I thought I should be able to prove this by running an application and basically trying multiple different configurations. And that's exactly what I did. So 4 years ago at MongoDB World, we talked about an open source implementation for a social network platform called Socialite. It's open source. I recently actually updated for the latest version of the driver, et cetera, et cetera. What it is it emulates Twitter-like service, and it comes with built-in benchmarking. So it's very easy to drive it with what's essentially a realistic workload, and its architecture looks like this. The user graph service is the thing that handles friend requests, who follows whom, and new users signing up. Then the content service is users posting things. And then the feed service is what reads data from both of them and creates a cache, essentially, logically speaking, of your latest, like when you log in, so that you see the latest updates from your friends or people you follow. And the reason it was architected the way it was is so that you could essentially scale each database, so each service takes its own URL, its own resource locator, and it'll go to a separate cluster or the same cluster, depending on how you configure it. It makes it very easy to benchmark things side by side. If you are actually interested in this, we have several talks recorded about this. It's a pretty fascinating example showing how you can vary your schema choices and your index choices and see a demonstration of how they actually scale better or worse depending on the type of workload that you do there. And of course, like I said, designed to scale horizontally. The most important criteria is latency, right? A user comes and clicks, show me what's going on. They can't tolerate a delay. And ability to scale the resources linear. So those are kind of the two main goals there. I generated a workload that was for about 1 million users, mainly because I was using Atlas and I didn't want to go above like M30 instances because, can only expense so much in the server usage. But it did work pretty much the way that I expected it. and I ran it with scenario 1, 2, and 3, and I gathered a lot of metrics. Among other things, I used our monitoring, our cloud monitoring, or Atlas has all the monitoring built in. So this is an example of what very tuned targeted queries look like. This shows ratio of scanned index entries to documents returned and documents to documents returned. That shows that pretty much half the queries are satisfied straight from the index, and the ones that do have to go to disk for the document only read, on average, about 1 document for every document returned, right? So we know there was no inefficiencies in the app side. The app was requesting things as efficient as possible. So I started running things, and I'll show you the hardware monitoring for scenario 1. And remember, scenario 1 is shard everything. So there are 3 shards. Each one of them have a third of our content service, user service, and the timeline cache service. So it makes sense that since the data was balanced evenly, the CPU and disk numbers were roughly the same on all 3. And we can immediately see here that the CPU is pretty pegged, and disk utilization, which is the middle on the bottom, is close to 100%. And the disk latency is not looking very good. So I'm looking at this and going, well, I'm going to need more resources, but how many more resources and what kind more resources? There's really very little information at a glance here to know what's the bottleneck, which of the 3, and how much of a bottleneck is it? In other words, maybe the thing that's putting the heaviest load is only a little bit ahead of the next thing, right? Maybe you need triple the resources, or maybe you just need a little more resources. And so compare this to 3 side-by-side charts from each service having its own replica set or its own individual shard. So first of all, this is CPU, and it might look the same because, you know, you're sitting pretty far away, but I can tell you that the first one and the last one are like in the teens, and the middle one is close to 100. And you may or may not be able to tell, but the one in the middle has a different color representing like about half of it. So this here is actually all I/O weight. So immediately you're going to tell me, okay, whatever was on shard 2 or that second, the middle system, that's the thing that's absolutely maxing out the disk probably, because the CPU is spending all of its time waiting for disk. And sure enough, if you look at disk for content, 5% utilization, 10 millisecond response time, that's not bad. For user, kind of very similar. For timeline cache, utilization is at 100%, and disk latency is at about 1 second. Now, when all 3 of those were sharded across 3 systems, there's no way to tease out this kind of information, right? You can look at logs, you can see what the most active collection is, but that doesn't tell you the orders of magnitude, right? That's the difference between the 3 services. So this is the kind of thing that can cause people to spend a lot of money for a long time before they realize that, wait a minute, fundamentally, these 3 services use resources differently. The timeline cache is something that updates fairly large cached documents frequently, and flushing them to disk seems wasteful because you could just get them back from the content collection, right? The cache could just go away. You can literally treat it like a cache. And actually, that's what I did. What I did was, I pulled out the timeline cache service from my clusters entirely, and I put it into a MongoDB in-memory storage engine that was running on the desktop server that was actually sitting under my desk. And this is the difference it made. This is combined operations, op counters, for the content service and the user service, or maybe I have them backwards, I'm not sure. But you can see that even though their resources didn't change, because I didn't let them use up the 3rd shard that the other 2, that the one service that I removed was using, right? Just the fact that they were no longer being blocked by the work of that 3rd service, the throughput jumped from somewhere in the 200 range to well over 1.5 thousand per second range, right? So moving the cache into its own cluster essentially created a scenario where now I could see the real workload that the other 2 services were using, having them all together essentially obscured that. This is, I just thought it was a really cool picture. The Atlas and Cloud Monitor has now a tab for real-time monitoring. So you can literally watch like the little CPU thing go and the operations are passing by, and it was just really cool to see. Disk utilization would occasionally spike, right, during flushing to disk. But then this is the same thing for in-memory. 1% disk utilization was the highest I saw it go, because I think that's what the logs, writing to the logs, was taking. So that was pretty cool. Now, real-life cases like that I see is when, for example, you have scenarios where you have very busy user collections, and reads from them must be serviced extremely fast. But then occasionally you have some information about user activity that you must persist, and you don't care if it takes a long time. But there's no way to say, here's a write, but only do it when things aren't busy. You just send a write and you hope it doesn't impact things too much. If that write is to a completely separate collection, which frequently it is, then that user data, the data that users read, it probably should go into a separate cluster, so that essentially you're not having to now service both reads and writes. Because normally, you size your hardware and you plan things to service one type of load, and a different type of load would frequently create a requirement for different hardware, which is at odds here. This is the before, 100 to 150 operations per second. This is the after for the cache service. And what I did is I did like a 40-minute experiment where I emulated like, ooh, the Oscars are on, or something exciting happened at World Cup, and 60 extra users just stormed the system to post something, oh, my team rocks, and then run away. So it was able to maintain pretty good sustain rate there. So very easy to see throughput. But what about latency, right? Throughput you can measure right there, but latency you kind of have to measure from the point of view of the application. Luckily, Socialite comes with benchmarks that capture latency like P50, 75, 95, 99, 99.9, and they put them in little CSV files, and I was very much dreading the part of this where I was going to have to like pull them into a spreadsheet and try to draw graphs and try to figure out. But then they told me that charts was ready for beta. It was awesome. I wasted so much time because there were so many different pretty pictures. Like even though like the first couple that I did, I could have just showed those, but it was really cool. Yeah. So right here I had all my all my latency rates. This is actually a throughput chart. This is a mean 15-minute trailing throughput rate, and for a particular like fixed time period. And then the different types of operations are color coded. You probably can't read it, but it's like because people can follow, unfollow, post, read, etc. This was my attempt at a latency scatter plot, where a different color represents different type of operation, size represents the number of them, the rate that they were happening during that second, and shape is the scenario, whether we're doing scenario 1, 2, or 3. It's impossible to read this, even up close, so I'll just tell you, scenario 1 lost pretty much every time. Sharding everything tends to make small blips affect everything and kind of cascade. So for performance was not great. Down below, that was scenario 3, 2 or 3, and the equivalent one for scenario 1 was like an order of magnitude higher, so I couldn't even fit them on the same chart. Oh yeah, actually I did manage to fit them on the same chart, but because we can't do log scale yet, but they tell me that it's coming, it kind of looks weird. And then I built the whole dashboard out of this, and this is why I wasted so much time, because charts is kind of fun to play with. If you guys didn't go to one of the 2 charts talks, you might want to catch the recording if you ever need to do any kind of reporting on your Mongo data, because it's so cool. All right, so I'm going to score this. Shard everything, scalability, capacity scaling, not so good. Separate clusters, much, much easier, right? You can scale them independently. You can use different instances. If you have a sharded cluster, it's a little trickier to try to maintain different hardware for different shards. In fact, even with automation, can get a little hairy. Debuggability definitely was not very easy. with shard everything was trivial with separate clusters. So now you might be saying, yeah, but how much workload can you put on one replica set anyway? I'm going to have to shard all of them anyway, right? So I decided I would go out and try to answer that question. And I found one right at home, at work. A couple of years ago, we gave a presentation about open source project we called MongoDB Continuous Integration System, MCI. We call it Evergreen now. This is the replica set that supports Evergreen, which runs thousands of tests every time there's a check-in for any of our code bases. And I don't know if you can tell in the upper right-hand corner, it has 20 terabytes of data in it. And the op counters add up to something between 15 and 20,000 operations per second. So, replica set, and this is not a massive server either. It's less than 100 gig of RAM, so it's not like one of those 400 gig massive servers. All right, time for another disaster story, because we're getting, out of time, and I hate to stand between people and beer. We were not able to start Mongo in primary mode. We accidentally deleted the DB directory, so they were running with an option called directory per DB, which is a way of having each database in its own physical directory. Sometimes it's done to mount the different directories on different file systems. However it happened, one directory got deleted. It's okay, they had a recent backup, but MongoDB won't start. Why won't it start? The backups were not taken correctly. I don't think I'm going to tell you exactly how incorrectly they were taken, because I don't want to give people any ideas. But what we know for a fact was they never tested their backups. And the most important part of taking backups is testing your restores. Try to restore it at least once for practice, right? So test your backups. No SQL not equal no DBA. And this one, I really had no trouble finding people doing this with every other database you can imagine. Yeah, Oracle, MySQL, Postgres, even Azure. You'd think it hosted all, but I deleted my site and it deleted the database that was associated with it. I didn't mean to. So these things happen. Just be ready for them. All right, so for availability and reliability, I'm going to say that shard everything is not good, because if you delete something accidentally and mess up one of your shards, you essentially messed up some percentage of every single collection that you have sharded, right? If you have a multi-tenant system, which, by the way, a lot of people use MongoDB to host some kind of a service, multi-tenant, they go, I'll just shard every tenant to every shard, and that way if some tenant is generating a lot of load, it'll get distributed, it'll get scatter-gathered is actually what's going to happen. And I say, really? So if that tenant is DOSing their own database, you really want them to DOS all of your other tenants at the same time? Or if there's a problem with one shard, do you really want it to impact every single tenant? And then usually they go, I wasn't expecting to be having problems with any of my shards. Does that actually happen? Yes, it does. So keeping things separate, yeah, it may seem like there's more management involved, but face it, all that stuff should be automated anyway, right? Nobody's actually provisioning things by hand, right? Right? No, you would not be doing things by hand, and I will tell you why you shouldn't be doing things by hand. You have stomach for a couple of more crazy stories? All right, so DBA adds a new shard. DBA observes that the data does not seem to be migrating to the new shard at all. So the DBA decides to fix the problem. I say fix because, as you might imagine, what they did not actually fix things. I say problem because there was actually no problem. Turns out they had a balancer window on. The balancer wasn't even scheduled to come on till much later that day. Anybody want to guess how they tried to solve the problem? Yeah, it wouldn't have been so bad. They decided they would, reshard the collection. I don't know, they thought maybe somehow the sharding information got lost, so it's not being balanced. But of course it doesn't work, because you get back an error that says already sharded. Simple solution? Oh, just remove the chunk information from the config database. I'm kidding, don't do that. That's a bad thing to do. Because now the sharded cluster thought that this collection was not sharded, and that the only valid data was on shard 1, and bad things happened. To keep a long story short, so my colleague was on site with them. I was on my computer and on the phone many, many time zones away, and we actually managed to recover majority of their data. Turns out they had good backups. It just took a while to get everything back. I don't think I need to draw any other conclusions. I also know that they did not have a test environment in which to try this. Otherwise, this would not have happened. This is funny. All right, they did send me flowers 3 months later. All right, we have about 1 minute left. You guys want to hear another disaster story? Here, I'll speed through this one, because this one was so basic it wasn't even funny. There's like 17 terabytes of data. It's all in one data center. They turned off journaling. They took no backups. There was a power failure in the data center, and there was no uninterruptible power supplies on any of the servers. Who could have anticipated that would happen? The moral of the story, bad things happen to good data centers. And they send chocolates. And I'll tell you my favorite story, which is really kind of scary, and it goes to show that even workload isolation won't save you from everything. We had a call that says DB stats is showing that the data size is bigger than file size. And this was before WireTiger. So data size can't be bigger than file size. In green is us. We say, really, their data sizes, that means data files are being viewed as missing by MongoDB. And then a little while later, they opened another case saying, we're seeing incorrect file size on numerous servers that we have. I went, really? That's strange. Well, do these databases have anything in common? In particular, do they have anything in common with the one you told us about yesterday that had more data than file size? They said, well, nothing comes to mind that they have in common. It did seem to all start like on the 28th, of course, because bad things happen when most people are on vacation. We noticed it all happening at the same time. We think something might be deleting data files. Do you guys remember a cheesy movie from the 70s, like cheesy horror TV movie called When a Stranger Calls? Where they go, we've traced the call. It's coming from inside the house. Yes, they told us. We deleted the actual database files on the primaries and the secondaries on December 28th. Why would they do that? Well, rewinding it all back, we find out what happened was somebody noticed that they're low on disk space. You see where this is going, right? Their solution was to write a shell script. It found every file on every disk, on every server, and if that file is bigger than 1 gigabyte in size and it has not been accessed for more than 3 days, then it would delete it. Which is really funny, especially when you consider that it didn't reclaim them any of the disk space, because as long as the process is running and holding a file handle open, the file is not actually going to be removed. So, you want to guess the outcome? How much data was lost? None. Actually, none of the data was lost. They got very lucky. They didn't shut down those MongoDB processes, right? So what happens is the files are still there. You just can't see them, and if you bring down the MongoDB process, the files will go away for good. It turns out that a running MongoDB can do something like db.repair. db.repair just copies your data into a new file, and then when it's done, it drops the original file. So we told them to do that, and they said, no, we can't do that. We don't have enough disk space. To which my boss said, can't they go to Fry's and buy a bunch of disks? Luckily, they found a couple of spare servers, and they were able to add them in turn to each replica set involved. And once it synced the data set over to a new secondary, they could now restart every other secondary, and it would resync the data set. So no files were lost, but yay. Hopefully we learn from this that it's not a matter of whether, but when a disaster will strike. The less impactful you can make that disaster, the better. And I hope you guys enjoyed today. Next is beer. Beer is actually not till 5:30, so the fact we ran a few minutes over is probably okay. If you want to come up and tell me your embarrassing disaster story, I love them. And I will see you out, where's the beer thing, in the pavilion?
Yeah, it's probably.
Yeah, in the pavilion. So, thanks.
So